Hello and welcome back. So in the last couple of videos, we started talking about the integration of complex functions, and we sort of reminded ourselves of certain ideas coming from vector calculus, focusing on the two-dimensional plane. So let's just see how sort of that plays a role into how we understand integration of complex functions. So to begin with, let's follow the same approach that we did when we started talking about differentiation of complex functions, which is we just take the idea of an integral, and as we know from integration of real function of one real variable, we just take that idea and see what it could mean in the complex domain. In other words, let's just think of this quantity integral over some curve C of a complex function wz dz, and see what this kind of a quantity could actually mean in the complex domain. So first of all, in terms of what this summation or what this integral means in a more technical way is that we just have some kind of a curve, or not in a technical way, but more in the sense of how should we think of this as a limiting process of summing over certain quantities. The idea is very similar to that of a Riemann sum. So we have some curve C, and we dissect it into small intervals, for instance in this manner, and each of these intervals is denoted by a complex number dz. So it has both a magnitude and a direction, and we'll assume that all these have similar lengths or magnitudes, but as we can see, the directions keeps changing. So let's say this is some dz at a point z in the complex plane. So for instance, this could be the complex plane, this is a curve in the complex plane, and this is some point z, and we've taken a infinitesimal complex number dz here. And then we evaluate the value of the function here, which is wz dz, wz. We multiply it with dz. Likewise, we evaluate the value of the complex function here, multiplied with the complex number dz there, and then we sum up all these quantities. And the limit of the summing up of all these quantities is what we mean by this integral. But this is just sort of a procedural way of how we sort of interpret this kind of a quantity. But our aim is to understand what this could mean physically. How do you give it an interpretation? So in the case of integration of a function of one real variable, the interpretation is that it's the area under the curve. So what is the corresponding interpretation of this quantity in the complex domain? And that's the reason we started talking about and reminding ourselves of ideas from vector calculus. So let's do one thing. Let's begin with this integrand here and just evaluate it and see what form it takes. So what does it mean to evaluate it? Well, we know that the complex function wz has a real part and an imaginary part, so we can write it as u plus iv, where u and v are both functions of x and y. So u is a function of x and y, and v is a function of x and y. Okay. Likewise, dz, the infinitesimal complex number, is dx plus I dy. And the integrand here is just a product of these two complex numbers in some senses. So the integrand, the product of these two, wz dz, is this multiplied by this. And so if we collect the real and imaginary parts, if we separate the real and imaginary parts, so in the real part we'll have u times dx, and then from here we'll have minus v times dy, that's one part, plus I times, we'll have u times dy plus v times dx. So whatever this integral is, if we integrate this, is an integral of this quantity plus I times an integral of this quantity. Now these two, essentially these two quantities that we now have in the integrand is quite suggestive in many ways, and the way to seeing that is now to invoke the interpretation of the complex function wz as a vector in the complex plane, and then let's see what happens. So let's just keep this in mind, that this integral, I'll just write it down here, integral, which is integral of wz dz, takes the form u dx minus v dy plus I times the integral of u dy plus v dx. Okay, Okay, now let's say this is the curve that we were talking about, and we are at some point on the curve here. So first of all, the complex number dz is, we can think of it as denoting, or as sort of lying along the tangent to the curve. So the dz complex number is along the direction of the curve, so it's like the tangent. Now if you want to use complex notations and denote the normal to the curve, the way we were doing it when we were talking about vectors in two-dimensional plane, so the normal could be would be some vector that will go like this. And in terms of complex number, it's quite easy to denote, it's quite easy to find what is the complex number denoting this particular vector, and that's because if the tangent is dz, then this vector is nothing but dz rotated by minus 90 degrees. And so this number, complex number, is nothing but minus I times dz, right? And this dz in terms of vectors can be thought of as dx comma dy. Okay. Likewise, what is I times dz? Well, if dz is dx plus I dy in complex notation, then I times dz is I times dx minus dy, and therefore minus I times dz will be minus I dx plus dy. So the vector that denotes minus I times dz, its vector notation, will have dy comma minus dx as the components. Okay, so that's one way to thinking about dz and the normal in terms of how do you sort of easily get their corresponding vectors by using the complex notation. So dz we can denote with the vector dx comma dy, which lies along the tangent to the curve, whereas this vector is dy comma minus dx. And at this point, if we think of the complex number wz, it is some vector, for instance this vector, which has components u comma v. Okay, so if we sort of I'll just put a link to the previous video on when we were calculating the circulation and flux of a vector along in a region of space, in two-dimensional space. If we apply that kind of a interpretation to this vector, and this being the tangent direction and this being the normal direction, then the flux, or let's just calculate the circulation first. The circulation that we'll get is the projection of this vector along the tangent to the curve. So if you were to calculate the circulation or the work done, let's write it down. Well, let me just shift this a little bit. So that's the curve. This is a vector direction given by dx comma dy. The normal is it's dy comma minus dx, and then we have a vector here u comma v. So the infinitesimal circulation or work done, let's just use the notation work done, is the projection of this vector along the tangent, and that will be u dx plus v dy. Likewise, the infinitesimal flux will be the projection of this vector along the normal to the curve, and that will be u dy minus v dx. Right? Now, if you look at these integrands, now we can see why this casting this complex integral in this form was quite suggestive, because if you look at the first term, it has a u dx minus v dy. That's suggestive of something like a work done, but not quite so, because we have a plus sign here. If this was a minus, we'll get exactly this quantity. In the same way, if you look at the imaginary part of the integral, we have a u dy plus v dx. Whereas if we calculate the infinitesimal flux, we have u dy minus v dx. So again, it's very similar, except that the sign is flipped. And this suggests that instead of working with the vector field u comma v, or instead of thinking of the complex integral as the total work done or the total flux of the vector field u comma v, if you think of a new vector field, if you define a new vector field, let's say E, which has components u comma minus v, okay, and if you think of a vector field which has components u comma minus v, then the work done and the flux of this vector field along this curve will actually give us exactly what we're looking for as the integrands of this complex integral. So let's just work that out just to confirm. So if instead of working with u comma v, so let's say u comma v was in this direction, which means that this is the u component and that's the v component, and this is our xy sort of plane. So this is the horizontal or the real part of z, and the imaginary part of z plane. And the initial way we have drawn uv is the vector field associated with wz is in this direction. Then essentially we are saying that this is the u component, this is the v. But now we are saying let's think of a field which has the same u but a flipped v. So the v is here, and so we are thinking of a vector field which is this. And in terms of complex notation, how do we get this vector field from here? Well, if wz is u plus iv, then what we want is a vector field corresponding to the complex mapping u minus iv, which is just the conjugate of this. Okay. So if we define a vector field associated with the conjugate of this, which is u minus iv, the corresponding vector field will have components u comma minus v, and then the work done by this vector field along the direction dx comma dy will be, the work done will be u comma minus v dot dx dy, which is u dx minus v dy, and the flux will be the flux will be the projection of this vector field along the normal to the curve, which is u dy plus v dx. And these are exactly the integrants appearing when we interpret the complex, when we sort of expand the integral in terms of the complex notation, in terms of its real and imaginary parts. Okay, so in other words, one interpretation of this complex integral is that it is actually along some curve C is actually that it is the flux crossing this curve of a vector field associated with u comma minus v, or rather the conjugate of wz. Likewise, the imaginary part of the integral is nothing but the flux associated is the flux flowing through the curve associated with the vector field which has components u comma minus v, which is the conjugate of wz. And if you move along the curve, the work done is also associated with the vector field E tilde, which is composed of the conjugate of wz. So how does this sort of help us in understanding a lot of the other results that come about in the theory of complex functions and complex integrals? We'll see as we sort of explore these ideas further. But this is quite interesting because this is sort of we have moved beyond just the procedural definition of an integral and sort of come up with a physical meaning of it by thinking of the complex function as a vector field. We found that if we think of a vector field which is not just composed of the real and imaginary part of the complex function, but rather is composed of the real part and the negative of the imaginary part of the complex function, we can actually think of the integral as composed of the real part of the integral as the work done by this vector field along a curve where we are integrating, and the imaginary part of the integral as the flux flowing through that curve, along which we are calculating the complex integral. So hope this sort of sheds some light into the meaning of complex integrals, and we'll carry forward this discussion in our future videos. So hope to see you soon. Thanks for watching.